Dear participants, ladies and gentlemen, welcome back to Stage Bob for our last block today. We have 3 more exciting presentations on quantum computing and quantum simulations in this block. And our first speaker in this block is Natalie Kilber. Natalie obtained a postgraduate degree in physics from Cardiff University and also BA from Hult International Business School. She's the CEO and founder of Nabla.co, that's her own advisory firm. Welcome, Natalie, welcome to Quantum Summit here on Stage Bob. And I hope you can hear me. You look a bit confused still. I hope you can hear me. And I'm looking forward to an interesting presentation from you called Ctrl N. Can we shortcut innovation? The stage is yours, Natalie. Welcome here.
Thank you for the moderation. And thank you for letting me be here. Well, let's jump right into it. To date, during the pandemic, we have to realize what our priorities are. A lot of processes and systems, especially social systems, have stalled. Some have changed. We learned to leverage remote access at unprecedented rates, and we still find new ways to innovate. Despite constant reminders that Moore's law trends are deteriorating, as have a number of related laws, including Dennard scaling, referring to power density, clock frequency, and Kuhne's law, and all of these are also remaining problems for quantum hardware design, by the way. And yet, advancements and innovations are still progressing in the form of specialized circuits and chips. One of the most promising fields is quantum technology. And here, almost like you can see the meters-long wiring for such a quantum chip. Ironically, this cryogenic enclosure is huge. And when we approach the event horizon of Moore's law, and I'm speaking nanometer scale, we leverage its own demise. This is exactly in the quantum realm. Single electron transistors, also called quantum dots, are just one of the many hardware flavors quantum computers come with. What is usually a micro-integration reliability engineer a nightmare for them, electron wandering of material breaking wires and electron tunneling through registers, missing them, rendering your computation unreliable. Yet, single electron transistors, those quantum dots, are the logical evolution at the end of classical computation. Volt or no volt, punched hole or no punched hole in punch cards, we've come a long way. Unlike in other fields, I'm glad physicists aren't deterred by laws and forecasts. So how do we access that potential? Is there an infrastructure for this, for me as a big, small, or even new business? Just as there is a plethora of unstructured complex data to harvest out there, I'm talking big data, so are the tools for harvest. We've been talking about 3 main setups during this conference, namely Quantum as a Service, CaaS, where you have the access through an IDE, platform, or API, and the hardware is abstracted away and maintained by the provider. It usually comes with a lot of higher-level libraries for models, but be aware what you need. If you're looking for quantum neural networks, so quantum machine learning, the learnability is low for systems that offer randomized qubit initialization. And you may not want a universal gate computer at all. You want a quantum annealer. And all depends on your use case. But all of these run under Quantum as a Service, CaaS. And then we have simulators. It's usually classical hardware simulating qubits up to the classical limit until the horizon of one quantum computation surpasses it. And earlier this year, AWS has simulated about 50 qubits. And on a laptop, it's a rule of thumb, you can run about 25 qubits. And these simulators are coupled in CaaS services. And sometimes you want them for resource estimation before you run anything on actual quantum hardware. Then in the third setup, we have bare qubits. And there you have the orchestration of the scheduling and routing and mapping of the qubits yourself. It's in your hands, often at compiler level, and calibration is often still giving you a performance boost. So you're so low in the stack. And I speak of fidelity too, that reprogramming an FPGA to run federated workloads would bring your application a better boost nowadays. And this is exactly why it is at the R&D stage. There are many more challenges. And when you shift the perspective, those are not challenges, those are opportunities, especially for people like us in business. There are domain-specific accelerators, and these are pushing the boundaries of computational speed up, such as accelerators in machine learning, FPGAs and networks on a chip that orchestrate those quantum computers as well. they're nothing else but an integrated circuit that needs a host CPU. And the same thing are domain-specific accelerators. And one of these is quantum computing. At the core of a quantum computer, even in our smartphones, we need certain chips to convert analog signals to digital signals and then digital signals to analog again. Speaking of a camera, speaking of audio signals, all of these need these digital to analog converters and analog to digital converters, or short DSPs for digital signal and processes. So these are all part of a quantum computer as well. And yet we have information theory proving mathematically some speedups that quantum computing is exponentially faster in some problems but they forget that real implementations have hardware limitations. We have clock cycle problems still, like in Dennard scaling, and many more. And when I'm speaking of these digital to analog, analog to digital converters, this is just one bottleneck why those theories of speedups don't get traction. And we do need math formulation for this conversion, usually with unconstrained binary quadratic programming. And some know it as QBO problems and HOBO for higher order problems and connectivity. And some quantum as a service providers offer that or are about to offer that soon. And it just depends how we frame these problems, because all is still hosted and orchestrated classically through that host CPU. And big problems are for scaling and algorithms due to this conversion as well. It's complex beyond the main setups, not only quantum computing. This includes an explosion of innovation in ML processes, icing machines, exotic chips like memristors. Out of all the possibilities, we need decision hygiene, teams and processes to verify our needs and know our biggest industry problems. This is all nice and rhetoric. Now I get to the core message. Can we shortcut innovation? Conditionally, yes. It all comes down to our risk appetite to explore the new. Know where we create our value in the chain. And let's talk about which steps need to be taken to make these challenges and to tackle them efficient and cost effective. So you can get to the juicy stuff and try out your use case, your challenges and your burning industry problems. And first, you need to identify your use case. And for that, you need interdisciplinary teams. You need to build a team that can identify your use case. That exact same team, secure your environment. You need to know your environment. You need to secure your system, and not just the system, you also need to secure a spot in the industry as well. And then you can evaluate it cloud natively. Bring your own problem, BYOP. And in order to know your problem and your challenges, you need the right people to shine a light on it. And here I'm describing an example for a task force that needs certain skills. So you need to test your own value creating processes. You have subject matter experts, and I'm talking trade knowledge is one of the things you effortlessly bring as someone who made it in the industry. That intrinsic value, leverage it. This is at the core, and build your team around this. I was speaking about math formulation earlier. Physicists come with pre-installed libraries of heuristics about the physical world, or you can use optimization experts, or both. Then you need developers who work with security in mind, or with networkers, depending on the level you want to operate on in the stack. And of course, you need communicators. But Steve Jobs has called translators to convey the needs across stakeholders and to be the interface between the technical world and your business. And on the other hand, they need to be a lubricant to facilitate the collaboration within the team and the rest of the organization as well. There are many more setups depending on your use case. And you may need wet lab scientists in the mix or engineers, psychologists for recommendation systems. The point is only you can build the team to leverage your intrinsic value. And then you need to know your environment, risks, threats, mitigations. There are trade-offs between costs and performance, between cost and security. Find your risk appetite and determine your needs and opportunities. Doesn't mean that you have to go and lift and shift everything into the cloud. However, you can use cloud native runs to test ROI acceleration for where you see value. Be the full-blown application pipeline where you need to configure DDoS protection for an external API with different security network zones. where your R&D team enriches the data back in the backend for computation for your application continuously. And perhaps shown here, you just need to administrate a cloud instance for an ML app, a CAS app, Jupyter Notebooks, or you just need to spin up some secure VMs to test out some business relevant or dummy data for your R&D team. You may even be interested at the lower stack, at the hardware level, with the need to secure FPGAs, where you run software in the cloud with a secure enclave, obfuscating your code towards the cloud provider, running cloud native functions, and you need them at low latency, and you do this by optimizing page walks. So you need to know your data and critical business processes that ingest it to assess that. And you can do all of this, pivot, change, rinse, and repeat without the extortion of your controllers. Leave CapEx behind and mix and match hardware and software until you've found what truly disrupts your industry. Innovate faster, shortcut it, disrupt it yourself. In the process, you may gain significant improvements through intermediate steps and insights that along the way you'll find the right approach for your use case. It might not be quantum for now, but you'll be able to assess that with these 2 steps you've already taken. Building the team, environment. And the good thing is, cloud is at your fingertips, anywhere. So once you've built your team, you identified, secured your system, you get into the exploration phase. You can evaluate quantum as a service for applications. You usually do simulators for benchmarks against the classical limit. And you can co-design domain-specific accelerators, just how a quantum computer is a domain-specific accelerator. You can influence new chip designs with killer applications or algorithms for your industry. You can leverage different hardware chips. There are many fab companies that do custom chips. And we have graveyards full of them. Just look at the stochastic computing in the 80s with Rascal. So explore what is needed for your problem. Is quantum part of it? In the future, with more computing volume, can a quantum chip perform better? Or is it even suited for a single sub-application? Shape your market. So there are plenty of technologies already out there in the quantum space, potentially disruptive, driving opportunities. We need to reap ripe technologies now. And when you have your task force, you know your data, you can iteratively verify technologies and explore. This space is vast. Your exploration needs to be documented and follow a decision hygiene. Some examples of the vast space contain MLCube, that is an offering by ML Comments, which is containers with machine learning models that you can shift without the dependency dread. We have quantum-inspired optimization, heuristic solvers. You have exotic chips for matrix multiplication and in-memory computation, which is a huge thing nowadays. These are called memristors. It's just one of them. Then we have in-data security. We can look at persistent storage. GitHub committed itself to actually use Project Silica and use 5D optical storage. You can store your data literally in glass. And the mean time of storage is about thousands of years versus magnetic storage, where you have a couple of decades. And that was a huge problem in the filming industry, because you need to preserve old movies and you have to store and restore them in hardware and in analog data. That could potentially transform a lot of things. And then we have in-transit encryption through photonic states. And it is quantum secure. We can use the glass fiber that we already have at potentially a lower cost. And without looking at endpoints, we're talking just the glass fiber. We can do in-transit encryption with photonic states that are compatible with quantum computing and QKD later, when we actually have a quantum internet, but we can harvest and use this technology now. Quantum is an opportunity, not a threat. And when you look at infrastructure, this is where we see the most adoption of quantum technologies. Test beds for quantum nodes, startups offering quantum metropolitan area networks, and satellite internet for the last mile of connectivity for 6G, and to bring the quantum internet closer to the world or lower orbit. So quantum months, transducers, satellites, DSPs as digital signaling processes, are all subcomponents and intermediate steps towards a quantum internet. Some will require trial and error to shape the market, and the technology that we'll need in the industry, those bottlenecks in the real world, they're often not represented in research test beds because you test against cases you define, and researchers may not have the information that business has. What is the actual bottleneck? What are the problems? What are our needs? And that collaboration is at the core. Lo and NIST demonstrated optical fiber used as a multiplexer to orchestrate a quantum computer, which was another bottleneck in quantum computing. So we used glass fiber to get into a quantum computer to try to curb the problem of these digital to analog converters. And many more. There's thermal, you have temperature problems in cryogenic quantum computers in those setups. And then John Preskill has teased that distilled states as a service, they will be an undeniable part of the quantum internet as a service, because the better quality of the states you need for a reliable service. There are many more developments happening right now. And you could check out the Quantum Internet Alliance in Europe, see what the future holds. Another problem or another opportunity why we build those teams is we're losing the researchers that we educate. Most of the top of the crop is going abroad because we are not building opportunities.
We have just lost the connection here. I guess you all understand that in this Corona crisis, you all are used to sometimes having breakups in online meetings. So this is just what happened here. We hope to have her back in a moment. So let's just give it a short moment. So far, I mean, we were almost through with the presentation, and I think it was so far a great presentation.